The next part of 4.2 is we're going to be using limits to calculate areas. So as you can see here on the screen, area is the limit as n approaches infinity equals the sum of I equals 1 to n of f of ci times delta x. Don't get too intimidated with this one. The ci is really just a right or left endpoint, okay, which we just calculated in the last few examples. So that shouldn't be too hard for us, okay? And then we have our delta x, which is b minus a. The one thing that you need to remember that we did before is remembering the limit, as x approaches infinity of 1 over x is 0. So we need to bring that back from when we did those limits at infinity before. So anytime we had a denominator where x was getting really, really large, alright, in the denominator it would go to 0. So that's kind of how we're going to use the limits in this function. And notice we're trying to get n to go to 0. Okay, so let's do an example here. And on your homework, you're going to be given a graph similar to something like this, and you want to find the area of the region bounded by the graph f of x equals x cubed, the x-axis, and the vertical lines x equals 0 and x equal 1. Well, that 0 and that 1, that's our a and our b on our interval. Okay, so you need to remember 0 to 1 is the interval in this case, and then f of x is x cubed. So what we want to find first is delta x, okay? But now we're not doing rectangles. We're going to leave it in terms of n and then take the limit at the end as n approaches infinity. Okay, so don't do any substituting out yet right away. We're going to leave stuff in terms of n first. It's I that we're going to substitute out, okay? So first step, as usual, find delta x. So it's going to be 1 minus 0, alright, because that's our interval, over n, so we leave that in terms of n. And then our ci, for ease of everything, let's choose the right-hand endpoint. Those tend to be easier. Our interval starts at 0, and then it's plus I delta x. Well, delta x is 1 over n, so it's I over n. So when we come down here and we substitute into the area is the limit as n approaches infinity of I equals 1 to n of f of I over n times 1 over n. Okay? So we're still doing the same concept here, but we're going to get all of our n's together, get them outside the sum, and then we're going to use theorem 4.2 to replace whatever i's we have. Okay? So notice we take I over n. Okay, that's our right-hand sum, or right-hand height, kind of the curve as we want to take an approach, and we substitute that into the equation. So we're going to take I over n, okay, and our original equation up here is f of x equals x cubed, so that's why in the next step here you see I over n cubed. We're replacing x with I over n, okay, and then we're going to multiply by the width here, which is 1 over n. So essentially, as we break this down, we're going to get I cubed over n to the 4th. Okay, so we have this whole limit here. The limit as n approaches infinity of I equals 1 to n of I cubed over n to the 4th. You should know the drill by now. Alright, we're going to factor out 1 over n to the 4th, and we're going to be left with the sum of I equals 1 to n of I cubed. Now what do we do with that I cubed? We use theorem 4.2 on page 2 of the notes. Okay, the sum of I equals 1 to n of I cubed translates down here to n squared times n plus 1 quantity squared divided by 4. So what we did is we rewrote that sum. We've done that in the previous examples. That shouldn't be any new knowledge right there. Alright, and don't forget to keep the 1 over n to the 4th in front. Now it really just comes to algebra, and then we're going to get down to where we can eliminate some things, right? Because we're looking for when we have a really big denominator, so that term can go to 0. So first thing for me, I squared the n plus 1, or FOILed it out, box method, whatever. So we got n squared plus 2n plus 1. Okay, and then I distributed the n squared through that trinomial. So we get n to the 4th plus 2n cubed plus n squared, all divided by 4. Now, here's the important part. Let's write everything with a common denominator. So I'm going to distribute 1 over n to the fourth to each term, and then I'm going to separate each term and have it over 4. Since the entire polynomial is over 4, I can write it as 3 different fractions over 4, and then distribute the 1 over n to the fourth. Okay, just some basic algebra there. So when we do that, don't get rid of the limit yet, we're not there yet. Limit as n approaches infinity of n to the fourth over 4n plus 2n cubed over 4n to the fourth plus n squared over 4n to the fourth. Now simplify. When we have n to the fourth over n to the fourth, it becomes 1, so we're left with 1/4 here, plus we have n cubed over n to the fourth. That leaves us with an n in the denominator, and 2 over 4 reduces to 1/2. Alright, we have n squared over n to the fourth. Remember, we subtract the exponents there, so we're left with 1 over 4n squared. Now we apply the limit. So remember, the limit as n approaches infinity of 1 over infinity is 0. So what happens? We keep the 1/4, okay, because there's no n to substitute in. When we substitute n, or infinity, in here where there's 2n, we get 1 over 2 times infinity, which is 1 over infinity. That term goes to 0 when we take the limit. Then we substitute infinity for n squared. We have 1 over 4 infinity squared. That also goes to 0. So that these two terms drop out and go to 0, and our answer is 1/4. So that's the area under the curve. It's 1/4. So what are we really talking about? We go back up here and look at the graph. If I were to find the area under the curve of x cubed from 0 to 1, the area is 1/4. And that's applying limits. Really kind of the same thing we did with rectangles, only instead of using n as the number of rectangles, we're using the limit as n approaches infinity. So there's not too much different math between the two. We're still getting everything simplified down in terms of an n expression. It's just now, instead of using number of rectangles, we're taking the limit as n approaches infinity. So we're trying to really get that expression broke down into like 1 over infinities and things like that, so we know that those pieces go to 0.